So the next part of this introductory section, again, we said it's very descriptive, not a lot of like lengthy problems, is to look at something called a critical value, or sometimes I do a lot of abbreviating in this chapter. I'll call them CVs. So when you hear me say critical value, some books call them critical points. So here's what a critical value is. First of all, it's an X value. So when you're asked to find critical values, you are asked to find X values. And they are going to be the X values where the derivative equals 0 or the derivative is undefined. So if we can look at these graphically. I'm actually going to talk to you about graphically, and I'm also going to talk about algebraically in this video. So we are going to look at a graph and figure out what would make it have a 0 derivative. So with a 0 derivative, keep in mind that is a horizontal tangent line. If it has an undefined derivative, that's when you're looking for like a sharp point. It's a great one that you're looking. There's other things, and we'll kind of talk about them, but those are the things that you're looking for visually. Now, it is when you see these, when you have these horizontal tangent lines. So let me kind of draw another picture up here. So let's say you have something like this. You're going to have a critical value here, whatever this X value is. We'll just call it A, because it has a horizontal tangent line. If I were to draw a tangent line, it would go like this. And you're also going to have a critical value here, because again, if I were to draw a tangent line, I would have a horizontal tangent line. Now you'll notice that both of those places where I drew horizontal tangent lines, those were extrema. Those were relative minimums, relative maximums. And that's what we're looking at, is your extrema are going to occur at your critical values, at those places where we have a 0 derivative or an undefined derivative. Now, it is possible to have a critical value that doesn't end up being an extrema. It doesn't happen very often. It's definitely less common. And that's this picture that's on the screen is a good example of that. At 0, we have a horizontal tangent line, but it doesn't actually end up being a minimum or maximum. It's like the graph kind of goes from going up, we would call it like increasing, and then for that split second, it just kind of hovers, and then it continues increasing. So we don't see like a change in the derivative. And we're going to talk about a lot about those things, about looking at the derivative signs and what's happening with those. So to find critical values, we're going to talk about how you find them graphically, and we're going to talk about how we find them algebraically. So to find them graphically, I have three options. The first two are very, very obvious. The third one is the one we just talked about, which is not very obvious, much more subtle. The first way we can look at a graph and know that we have a critical value is we can see those peaks and valleys. We can see those places where the graph goes up and then comes back down, or vice versa. So in that first picture, we have three places where it happens, and I'm just kind of approximating. It is nice on Delta Math. You can actually like see a scale. And the reason all those places are critical values is they're all places where we can tell that we have a 0 derivative because we have a horizontal tangent line. The second place that we can have critical values, it's also pretty visually obvious, is anytime we have a sharp point. I also use the word cusp. So if you see the word cusp, it's just a fancy word for sharp point. And these happen a lot with absolute value graphs. They can also happen kind of curved. You can have a graph that like looks like this, like it looks like the path of like a bouncing ball. That point, that sharp point or cusp, is again a critical value. And the reason is because it's a place where the derivative is undefined. And then the third option is the one we just mentioned on the previous screen. Anytime you have a place that has a horizontal tangent line, even if it doesn't end up being an extrema, you will still have a critical value. And the reason is because it's a horizontal tangent line, so it has a 0 derivative. This happens a lot with cubic graphs, like x cubed has that point right at the origin that has that kind of moment where the graph isn't going up or down, it's just kind of staying constant. Those are very difficult to see, and sometimes they'll actually tell you in words that that's a place where you have a horizontal tangent line, because it is so difficult to actually just see with the naked eye. So those are how we find critical values graphically. But then how do we find them algebraically? So if I want to find them algebraically, kind of three things happen here. First of all, you have to be given the function. So instead of a picture, you're actually given an equation. Then you have to take the derivative of that function, because we know critical values are places where the derivative is 0 or derivative is undefined. And then we have to solve that. We have to set it equal to 0, or see, does anything make it undefined, so that we can actually list potential critical values. Now, functions can have many critical values. They can also have none. The higher the power of the exponent, the more likely that you are to have many critical values, because higher powered functions tend to change a lot. They go up and down and up and down. And the more I increase that exponent, the more it has those, we call them turning points in algebra. So with these two, derivative is 3x squared minus 9. That will never be undefined. And really what you're looking for undefined is you're looking to see, is there a denominator that could equal 0? But we can set this equal to 0 and see when we have a 0 derivative. I'm going to factor out a 3. And so when I do that, I get x squared minus 3. And that means that there are two places that equals 0. That's going to be at plus and minus root 3. Critical values don't have to occur at whole numbers. They don't have to occur at like 3 or 5 or 7. They can occur at decimal values. In this case, you end up with like a positive square root of 3 and negative square root of 3. They can show up at fractional values, and positive and negative, obviously. Next one, power rule, power out front, power 1 less. So we get 2 over 3x to the 1/3. Now that will actually never equal 0. I'm going to make that, because I can't get the top to be 0, but it can be undefined. If x equals 0, we get an undefined derivative, or a vertical tangent line, and that is a critical value. So we do have a critical value for that one, and we have two critical values for the one before. Probably the most common mistake that students make is they forget to derive. And I know that sounds silly, but I've seen students give someone like this, where it was like x plus 2 over x minus 5. And instead of actually going through and doing a quotient rule to derive this, they'll just look at it and go, well, I know what makes that 0. Keep in mind, until you have the derivative value, you can't start evaluating what will make it 0 or what will make it undefined. So as silly as that sounds, make sure when you're doing these algebraically, you always take the derivative first, and then analyze what will make that derivative 0, what will make that derivative undefined. And again, you can have many critical values or you can have very few. And that is kind of the overall idea of a critical value.